Okay, so chapter 5.1 notes the mean value theorem. So it says the mean value theorem is used to justify conclusions about a function over an interval. So right here on the definition, it says if a function f is continuous over the closed interval a, b, and differentiable over the open interval a, b, then there exists a point C within that open interval where the instantaneous rate of change equals the average rate of change over the interval. In other words, we have this equation. F prime of C is equal to f of B minus f of A over B minus A. This shouldn't be new, right? We've used this equation in so many different units. Okay, we're just basically building on top of this of all the different ways we can use average rate of change, slope, derivative to make interpretations. Okay, I would make sure you have two different colors, so maybe your pencil and a marker when I'm going to draw the diagram off to the side. Okay, so how would this look visually? So if we were to graph this visually, we would have our points A, B with the corresponding y values of f of A, f of B. Okay, so here's our first point, A, f of A, and our second point, B, f of B. And that is going to create or connect some sort of function. Let's say we have a function that looks like this. Okay. Well, based off of this theorem, what we're trying to find or what we're trying to estimate is the slope of between these 2 points on this graph. So we're trying to find this right here. Okay, and what they're saying is once we find that slope, we can use values such as C1 and C2, which you'll notice is going to be on the relative maximum and relative minimum of these functions. And we can approximate those slopes and use those approximations to estimate our slope of our function that would be in between those two blue lines that I drew, okay? So they're saying if we can approximate the slopes for the point C1 and C2, we can find an estimate for the slope of our function, okay? And again, that brings us to that equation f prime of C. We're talking about the derivative, which we know is the slope, okay? So in the first couple examples, it's just going to have us practice finding average rate of change and showing how we can set instantaneous rate of change equal to average rate of change. Okay, so number 1 says use the function f of x equals negative x squared plus 3x plus 10 to answer the following. It says on the closed interval 2 to 6, what is the average rate of change? So what it wants us to do is use the equation f of b minus f of a over b minus a. And in this case, a and b are going to be that 2, 6. So this would be f of 6 minus f of 2 over 6 minus 2. Okay, so how would we find f of 6 and f of 2? Plug it in. So we have f of 6 is equal to negative 6 squared plus 3 times 6 plus 10, which is negative 36 plus 18 plus 10, which is negative 8. Okay, we're just plugging it into f of x. And then we have f of 2 is equal to negative 2 squared plus 3 times 2 plus 10, which is negative 4 plus 6 plus 10, which is 12. So then I have negative 8 minus 12 over 6 minus 2, and that gives me negative 20 over 4, which is what? Negative 5. So again, this is the average rate of change. Part B says on the open interval 2, 6, when does the instantaneous rate of change equal the average rate of change? Well, since it's telling us to find instantaneous rate of change, we know we have to do what to the original function? Take the derivative. So we have our function f of x is equal to negative x squared plus 3x plus 10, which means the derivative is going to be equal to negative 2x plus 3. So again, it's asking to see if the derivative is equal to the average rate of change. What did we find the average rate of change to be? Negative 5. So we're seeing if negative 5 is equal to negative 2x plus 3, which since we're trying to solve for an x value, we're trying to see which x value makes this true. So in order to do this, we're going to solve for x, and we get x is equal to 4. Because we would subtract the 3 over, and we get negative 8 is equal to negative 2x. Divide by negative 2, we get a positive 4. Okay, so at x equals 4 on the interval 2 to 6 is when instantaneous rate of change equals average rate of change. Okay, so any questions? Yes. I subtracted 3 over and got negative 8 is equal to negative 2x. Divide by negative 2 and got 4. Okay, so now we're going to look at mean value theorem versus intermediate value theorem. Okay, so again, we know mean value theorem is that the derivative or instantaneous rate of change must equal the average rate of change somewhere in that interval. And again, when we're talking about that, we're talking about some function, right, that crosses through some points. Okay. And we approximate those using the slopes of the relative maximum and minimum values. Okay, same diagram we drew above, so up to you if you want to draw it again. Okay. Versus intermediate value theorem that says on a given interval, you will have a y value at each of the endpoints of the interval. Every y value exists between these two y values at least once in the interval. So what this means, it's saying, okay, I have a function, and on the endpoints, which are establishing that interval, somewhere between there on the function, I'm going to have some value of y that exists. So all those dash marks are representing a point or a value y that would exist on that interval. So that's the difference between the two. One is talking about how our derivative has to be equal to the average rate of change somewhere on that interval, versus one is saying, okay, on that interval, on that function, there's going to exist some value between those two endpoints. Okay. So typically, you're not going to see problems that look like this. They're not going to say find the average rate of change, find the instantaneous rate of change, right? They're going to apply those to applications. Okay, so for example, number 2 gives us a table of values. The top row is t represented in minutes, and the bottom row is h of t representing feet. It says a hot air balloon is launched into the air with a human pilot. The twice differentiable function h models the balloon's height measured in feet at time t measured in minutes. The table above gives values of h of t of the balloon at selected times t. So part A says, for t between 5 and 15, must there be a time t when the balloon is 50 feet in the air? Justify your answer. So here it's not talking about velocity. It's not talking about acceleration. It's just talking about the position function, which means we're not asking to take the derivative. We're trying to see first if this function is continuous and see if we can use IVT to justify. Okay? So the important part in this problem, it says that the function is twice differentiable. Okay? So I'm going to say the answer is yes. Okay? And I'm going to start off by mentioning how the function h of t is continuous. Because we know if a function is differentiable, then that applies it must be continuous. So we would say, since h of t is twice differentiable, okay, this implies h of t is continuous. Okay, that's the first part in order to continue using IVT as our justification. So we would say, because it's continuous, we can use intermediate value theorem that implies that there exists a t where t is between 5 and 15 such that h of t is equal to 50 since, and then we prove this, we have to look at the values of h of 5 and then h of 15. So since h of 5 is what value? 40. And h of 15 is 70. So this implies that our value 50 that we were trying to find is going to be between 40 and 70. Okay, so you're not able to answer yes or no until you come to these conclusions, right? So if you wanted, you could go through this whole process first, right? Ignoring where I put yes. Go through the whole process, and if you get something that makes sense, then you would go back and write yes. Or if you get something that does not make sense, then you will no longer have something that says there exists a t where t is between this interval. Instead, it would be there doesn't exist a t. Okay, so you'd go back and say no because of the following. You'd still have to use the justification. Okay, part B says for t between 20 and 30, must there be a time t when the balloon's velocity is 1.5 feet per minute? Justify your answer. So here, since we're talking about velocity, that's how I know that I'm going to be using the mean value theorem. Because velocity is the derivative of the position function. But are we given the function in this problem? No, so how are we finding the velocity? Average rate of change. So we're going to use the formula that velocity is equal to h of b minus h of a over b minus a. And since we're looking at the interval from 20 to 30, then we know what our a and b values are going to be. So we would say h of 30 minus h of 20 over 30 minus 20. And then we would plug in the values from the table. So what is h of 30? 80. And what is h of 20? 65 all over 10. So 80 minus 65 is 15. 15 divided by 10 is 1.5 feet per minute. So since we were able to get velocity to equal 1.5 feet per minute, which is what they were trying to find, do you think that this answer is yes or no? Yes. So we would say yes, and we still have to talk about, since it's differentiable, implies continuity, so we would say yes, h of t is twice differentiable on the open interval 20 to 30 and continuous on the closed interval 20 to 30, which implies by the mean value theorem, there exists t from 20 less than t less than 30 such that the derivative of h of t, which is equal to velocity, v of t, is equal to 1.5 feet per minute. So I use the definition of the mean value theorem to answer this question. Okay? If you go back and look at the definition, it will talk about it being differentiable on the open interval and continuous on the closed interval. So I had to talk about those first before mentioning the mean value theorem itself. Okay. What if when I solve velocity, I didn't get 1.5 feet per minute? You would say no, right? We can't guarantee by the mean value theorem that this would be possible because we didn't get the same value for velocity like it was asking us to.